Hello everyone. We are going to continue with our lectures on analog integrated circuits. Today lectures is about linearity. The outline for today's lecture is first we're going to talk a little bit about linearity, general concepts. Then I'm going to explain what is static nonlinearity. Then we are going to talk about how feedback affects nonlinearity. Then we're going to talk about the nonlinear performance of the different configurations that we have studied. In particular, we are going to touch what happens when we have balanced configurations or differential pairs. Then I'm going to talk about dynamic nonlinearity and show some examples. So we have already been talking about how noise and nonlinear distortion appear in amplifying chain. So we were talking about that the first stage is normally responsible for noise. So the noise that the first stage adds is going to be amplified, and then it will basically dominate. A similar observation, we can see that the amplitude of the signals at the output of the last stage are normally very large in comparison to the previous stages, and then it is the last stage, the one that it is going to define the linearity performance of the whole system. So linearity is going to be basically dependent on the last stage. So all the stages will have some nonlinearity, but normally it is the last stage, the one that it is much more affected by nonlinearities. So this is the one that we are going to put a lot of effort during design. So when we talk about nonlinearity, basically we talk about two types of nonlinearity: the static and dynamic nonlinearity. And for the static linearity, what we're going to concentrate it is just on the characteristics of our transistors, and then basically static characteristics, DC characteristic curves. As we have seen before, the transistors work as amplifiers thanks to that they are intrinsically nonlinear. So that we have this exponential dependence at weak inversion and quadratic dependence at a strong inversion. So they will introduce nonlinearities in our amplifier chain. So the static nonlinearity consists on studying this kind of nonlinear behavior. Then the dynamic nonlinearity, it is related to linearity that it is produced by components that have memory, for instance capacitors, that, as we have also studied before, in many cases that are nonlinear. The intrinsic capacitors in a transistor, they depend on the inversion coefficient, and then they exhibit nonlinear behavior, and those ones need to be dealt a little bit different. So the transfer characteristics are intrinsically nonlinear due to the nonlinearity in the devices, and then we remember what we did during the first lecture. We have that we plot the input and the output voltage or currents. It can be any amplifying quantity. We plot these quantities. We will have the following curve in. So we will have at around the operating point, that it is the place that we're going to be working. We have some weak distortion. So and then when the signal excursion it is very large, at some point it will take values that approach the power supply. So at some point we are going to hit the power supply of our system, or if the signal excursion it is very low, it will hit the negative power supply, in most of the cases ground. So we are basically limited by the power supply in most of the cases. For linear amplifiers, there is family of amplifiers in which this is not exactly working like that, in power amplifiers where you can go above the power supply, but we are not going to touch these kind of amplifiers in this course. So for linear amplifiers, what we have is that we have a limitation in the signal swing at the output, that we cannot exceed the power supply VDD. So when the signal approaches VDD, what we have is that the amplifier is going to clip. So we will see that the output is just going to clip, and then we call this a clipping distortion, or that it is extremely strong distortion. Basically the signal is going to be cut. Now for most of the analysis steps that we do during design, what we do it is just move this curve to the origin. So we remove the operating point, that offset, and then we just linearize the circuit around the operating point. So we have to be very careful. This is just an assumption. It is just a simplification that makes our analysis possible with linear system, considering as a linear system. So we can use Laplace transform, Fourier transform, superposition, and other tools that are very handy. But remember, this is just a simplification. In reality, we have to work with a nonlinear system. So the static nonlinearity, as I mentioned before, it will depend on the nonlinear behavior of the transfer course of the transistor, this drain current at weak inversion, or moderate or strong inversion. And these nonlinearities will produce gain deviation, and they can be easily estimated by using simulations, DC sweep simulation, as I'm going to show you very soon. We are, due to the fact that, we are just analyzing the nonlinearity produced by the transistors, by the transfer functions of the transistor, the output characteristics of the transistor. We are not taking in consideration the capacitors. So it is just one part of the nonlinearity. Yeah. So we bring this as an important topic because it is extremely easy to simulate and it is extremely easy to extract. And so normally we do this very early in the design process. For extracting the gain, if we have, I'm going to assume that we have already removed the operating point, so we have the in and the out in case of a voltage amplifier. So to extract the gain, what we do is to derivate this transfer curve, and then when we derivate this transfer curve, what we're going to see it is that derivate is going to look like something like this in many cases. So we see that very strong inversion or clipping very strong distortion or clipping distortion will happen at the borders, and then when the system is entering weak nonlinearities, we will have that. We will get the nominal amplification, the nominal voltage gain that we are designing for, and that is typically centered around the origin of our system. So we derive this signal and then we obtain the following curve, and that is the one that we have here, and then we can extract an error. So the operating point it is located here. The operating point is located here, and this is the gain at the operating point, and then an excursion, positive excursion x2 from the operating point will have a different gain, and then we can calculate the error of this gain using the following formula. We can do the same for the negative excursion that will produce a different gain, so we can calculate these errors, and these errors are going to be very handy. Now this is done very easily because extracting this curve we just need a DC sweep simulation. Okay, with a DC sweep simulation, so extracting these errors is very, very simple. Okay, so how do we use these errors? Well, we're going to do a little bit about the math first. For a nonlinear system, a weak nonlinear system, and again we can just plot our system like this. So for weak nonlinearities, the nonlinearities that are around the operating point, we can assume that the transfer function approaches a third order polynomial. So we can assume that we have this Taylor polynomial for this transfer function, and then typically we want to process these signals, for instance sinusoidal signals coming to the system. They're going to come to the system and they are going to produce and output voltage. So they're going to produce this kind of output. Okay, so sorry, this has to be like this. Okay, so they are going to produce this kind of output that is going to be nonlinear, and if we introduce this amplitude as Vm, this signal, at the output we will have the following expression here, which depends on all the coefficients of the polynomial, and then when we expand the square and third order components, then we will have a larger equation that, as we see, has components at the fundamental frequency, it has components at DC, second order, and third order. And we just group them. We will have that first the component at DC, will appear here. Okay, so this is the first component of DC. We have one of the fundamental, and very interesting. The component of the fundamental frequency depends on coefficient A that we expected, but also it depends on the coefficient C, that it is the third order coefficient for the polynomial, and normally this is negative. This coefficient is negative. That already tells us some very interesting information. For very large values of Vm, the signal is going to show some compression, okay, because this part is going to become negative. So it is going to show some compression when I increase the amplitude due to this third order nonlinearity. Then we have a second order component. So the second order component is located here, and then it depends as expected from the coefficient B, and the third order, a third harmonic located at omega 3, and then it depends on the coefficient C. Okay, so this is going to happen when we pass singleton omega 1 to this nonlinear system. Okay, so these tones that appear at the output are going to degrade the signal quality, and then we have to define figure of merit that allow us to quantize this error, this non-ideality in our amplification, and for that we have one that it is called the total harmonic distortion. And then for the total harmonic distortion, what we define is distortion levels. Okay, so distortion levels, and then we take, for example, these two distortions, the second order and third order distortion. So this is the second order, and this is the third order distortion. What we do is that we find these levels D2, D3 in decibels. So this is D2 and this is D3, and then we express these ones in decibels, and then we have a very good idea of what is the distortion level that it is produced at these frequencies. The total harmonic distortion, it is defined as the square sum of these distortion levels as factors, so as we can see here. Yeah, then we take it mathematically with the equations that we saw in the previous slide. The second, the D2, the second order distortion, will take this value, and the third order distortion will take this value. But in practice, I mean, we don't have access to these coefficients easily, and then yeah, we really don't find the values of B and C during our circuit design. What we do is something different, assuming that we pass this amplitude, this amplitude Vm cos omega 1 t to our system, the amplitude Vm. We can calculate instead an error for the positive excursion of Vm. Does it this is that is plus Vm, and this is going to be minus Vm. So we can calculate the errors for a positive excursion Vm and an error negative for a negative excursion of Vm. And then we do the math. We can put this distortion as a function of the errors instead, and then we get the following expressions that are extremely handy. The second order distortion can be expressed as the error plus minus the error minus divided by 8, and the third order distortion as E plus E minus divided by 24. And again, this can be extracted very simply, and I'm going to show very soon in an example. Another figure of merit that it is commonly used in radio applications is the intermodulation distortion. In radio signals, typically we have a lot of interference, and then signals appearing at different frequencies can produce intermodulation products that fall in the band of interest. So it is important to analyze what happens with more than one tone it is present in the system. So typically those tests are done with 2 tones, and then what happens when we pass 2 tones to the system. So we do the same thing. We pass 2 tones with an amplitude Vm at different frequencies, frequency omega 1 and omega 2. And then at the output of this amplifier, we will have different harmonics. So we identify the fundamental tones that we introduce, amplified, and then we have the second order intermodulation. There is one that will appear at high frequency. Normally we don't care about this one because it's going to be filtered, but there is one appearing at baseband, or that might appear very close to baseband, and that is serious. That we we call this one IM2, this intermodulation distortion. And then there is going to be also component on DC as we expected. And the third order, actually the third order intermodulation will appear very close to the fundamental. So we will have these ones, and again we can express these intermodulation products as a function of the errors. The errors, and we have the following expressions. Okay, so let's take a look at an example of how this work in practice. So I have prepared MATLAB script in which we have a polynomial. We have a gain of 1, and then second and third order coefficients for the polynomial, and then an amplitude. I put just an amplitude of 0.5, and then what I will do is that I will pass a sinusoidal wave to this nonlinear system, and then we are going to analyze the distortion both with the transient simulation and with the equations that we have just show you. So we run very quickly this simulation, and then we have first here what I do is I differentiate the nonlinear equation, so to obtain this gain. So I differentiate and obtain this curve here, and then with this curve I can extract the errors. I put an amplitude Vm equal to 0.5. So first I get the gain at the operating point, I get the gain at an excursion of 0.5, and I get a gain at excursion of minus 0.5, and then I just take these numbers, and I take these numbers, and then I just calculate the errors, the second order distortion, third order distortion, and then I put this one in decibels, and then the result of that simulation give me the following distortions. So the second order will be at minus 38 dBs and minus 50 dBs. Okay, that is what it is predicted by those equations. Now at the same time I just simulate this signal. I simulate this signal over some long time, and I will extract the spectrum of this signal. So you see this is a 0.5 volt signal that is entering this nonlinear system, and then I extract the spectrum of this signal using an FFT. So we have the spectrum, and then we can calculate the distortion levels in this signal. So we take the fundamental, we put a marker in the fundamental, and let's take a look. The second order distortion. So we have the second order term here, and then we subtract these two. It is minus 6 dB the fundamental, the second order distortion is minus 44, so it is minus 38. So it is exactly what it is predicted by my equation. And then if I take the third order is minus 57. The fundamental is minus 6. So this gives me minus 51, around minus 51 dBs. The equation predicts minus 50 dBs. So it is very close. It is very close. The simple calculation for static nonlinearity. It is very efficient, very accurate, very close to what the transient simulation and spectrum analysis tells me. But it is much more easy. I just need to derive the DC component, the DC gain. Okay, so we know that we can use this equation. Then we can test it in Cadence.